Good morning, everyone. So today, I am on a travel, so I cannot be give the lecture in the classroom. So I make the video like tomorrow. The teaching assistant will play this video. So uh, yesterday we learned the raster calculations, raster analysis. Let me share my screen. So we learned REST data spatial analysis, uh, and we learned three types of the raster data analysis. So the first one is local analysis, pretty simple, and the second one is neighborhood operations. The third one is zonal operation. The global operation is one very special type of zonal operation. So the for the local operations, the pixel value in the output layer will only depend on the pixel value in the input layer at the same location. So that's the local operation. It's very popular, like what you did in the lab. Uh, we calculated the difference between the pre-fire NBR and the post-fire NBR. The difference, that's DNBR. The DNBR, that's the represents the fire severity. So for that kind of operation, it's a local operation. The value in the output layer only depends on the value in the input layer at the same location. So the second one is the neighborhood operation. It's more complex. So for the neighborhood operation, it depends on the moving window. Usually we use the 3x3 moving window, or 5x5, or 7x7 moving window. In the calculation, the pixel value in the output layer will depend on the pixel value in the input layer at the same location. At the same time, it also depends on the pixel value in the neighbor pixels. Okay, so the last one is zonal operation. For the zonal operation, we first separate the input layers into multiple zones. Like in this example, uh, this example, we have three zones: zone 1, and zone 2, and zone 3. After we separate them into multiple zones, then we calculate um, the value in each zone. So we are going to talk about that in details later. So for the local operation, we learned that four types of local operations. The first one is mathematical function, like we did addition, subtraction, calculate absolute value, calculate the square root, power. They are the mathematical operations. Like well, what we learned in the lab, we calculated the difference between the pre-fire NBR and post-fire NBR. That's very simple, and that is the mathematical functions. And the logical function. For the logical function, like we make the comparison between the two input layers. And we are going to see if the test is true. If the test is true, then the output will be 1. If the test is false, then output will be 0. Reclassification. Reclassification is kind of similar to the logical operations. And first, we do the logical operations. We make a test. Like in this example, the test is if layer A is less than 3. And then if the result is true or yes, then we are going to use the data from layer B, because here's the layer B. And then if the test is false, then we are going to use the data from value in layer C. The example, let's use this one as example, the 5 here. First, we make a test. Compare 5 and 3. 5 less than 3, the result is false, right? So it's a no. So we use the value from layer C. Here at the same location, this value in layer C at the same location as B. The value is B is here. So in the output layer, in this location, the same location here, the output the value in the output layer will be B. Next, we learned the nested operation. So nested operation is kind of simple to understand. We just combine multiple operations together. That is a nested operation or nested function. Next, we learned the neighborhood operation. So neighborhood operation depends on the moving windows. So the moving window here in this example is 3 by 3 moving window. So the moving window then first start from the top left corner, and then after the calculation for the first 9 pixels, then the moving window move right to here, this place, and then move to the right again, then move to right until to the end of the first 3 rows, and then it move to the next 3 rows here, then move to right, then to the go downwards until to the last 3 rows here. Then the moving window will move right, then to here. So when the moving window move to this place, so that's the end. Okay. So for the moving window, we can calculate the mean of the 9 pixel value. We can also calculate the median or get the minimum of the 9 values, get a range and the maximum of the 9 values. In this case, for 1, 2, 3, 3, 6, 3, 3, 9, 3. So the median is 3. The mean is 3.7, and minimum is 1, maximum is 9 here. The range is 8. So this is from the minimum to maximum. The range is 8. For next week, we are going to learn the topographic analysis. We are going to calculate the slope, the aspect. For the slope and aspect, it's kind of difficult. We are going to learn it in next week. For the slope and aspect, it often depends on the neighborhood operations. We often set a 3 by 3 moving window. We are going to learn that next week. So next, let's take a look at this example. This is our input layer, and it's 6 by 6, 6 rows and 6 columns. Here is our input layer. Now we are going to apply a neighborhood operation on it. And for this neighborhood operation, we use a 3 by 3 moving window. Here's our 3 by 3 moving window. And within the moving window, we are going to calculate the minimum value for that 9 pixels. So first, the moving window is at this place. Here, that's our moving window here. Then we are going to get the minimum value for this 9 pixels. And then we can see that the minimum value for the 9 pixels is 0, right? This one is the minimum value in the 3 by 3 moving window. Then here, this place is the center of the moving window. Then in the output layer, the center of the moving window, the value will be the minimum value of the 9 pixels. Here, 0 is the minimum value within that moving window. So here, the value of 0 will move to here, this place. So that is our output layer. Output. So here's our input layer. After we get the value 0, then our moving window will move to right. Here, this place will be our new moving window. Include another 3 by 3 pixels. I'm going to okay. So Okay, now our moving window is at this place. Move to the right. That's a new location for the moving window. Then we do the operation again. We find the minimum value in the 9 pixels. This time the minimum value is 2, right? So now at this place, that's the center of the moving window. We are going to use 2, move 2 to this place. Right, the same thing for like if our moving window is at this place, move to the end of the first 3 columns. Now, if our moving window is at this place, we find the minimum value is 4, right? So 4 will be moved to this place. Then we get the value for the second rows. So 0, 2, 3, 4. Now I will give you 1 minute to see if you can get the value of this pixel. Now I use a question mark to block the value, and you can have 1 minute to test if you really understand the moving window. All right. To get the value of this pixel, then we need to know where is our moving window first. So if that's the center of the moving window, then our moving window will be at this place, right? That is the location of our moving window. Then we are going to use this 9 grids or pixels. So that is our moving window, right? So next we are going to find the minimum value in the moving window for the 9 pixels. So 22 is the minimum value. And so if we then we can get the value for this pixel will be 22. So because that is the minimum value for the 9 pixels. Now let's move to the next one. The majority, this time we are going to see another example. This is majority filter, majority moving window. The same thing, we first apply the 3x3 moving window to here, this place. And we are going to find which number is the majority. Here we have 1 and 2 here. We have 4, 1, and 5, 2. So 2 is a majority. So here, the 2 is the majority here. And then our moving window moves to the right to this place. And then this time we have 1, 2, 3. So 2 is still the majority. So I will give you 1 minute to see, to estimate, to calculate what is the value in this pixel. All right, to get the value pixel here, we need to understand, we need to know where is the moving window. So here, if that is center, then we know this is center, right? So our moving window is at this place. Here's our moving window, include the 9 pixels. So here, within this moving window, we have 1 and 2 and 3. There are 1, 1, and 3, 2, and 5, 3. So 3 is a majority. So the pixel value in the question with question mark, that will be 3. Okay, that's a majority filter. So the neighborhood operation is very useful in GIS. Let's take a look at this example. In this example, we are going to use the majority filter and to remove the noise. So this time we are going to use a cross, this shape. This is our moving window, not 3 by 3, 5 by 5, but a cross. So the moving window can in any shapes, 3 by 3, 5 by 5, even cross. It also works. So now we have one input layer. This side is our input layer, and here's our output layer. So that is the land cover type. In this error, we have 4 land cover types. We have a road, it's a black color, black pixel is the road. So we have a light gray color, that's the corn. And the dark gray color, the soybean. And the white pixels, that's other land cover types. So we use the remote sensing to do the land cover classification. But sometimes we can make mistake. The remote sensing can make mistake, or the software make mistake, or the reflectance does not follow the spectral signature curve. There's one problem. Look at this. In the soybean field, right? We see that there are several pixels. They are light gray color. They are corn, right? In the reality, it's almost impossible. We have one soybean field, and in the middle, very small area, we plant corn. Impossible, right? Nobody do that. So that is very likely to be a noise, or the remote sensing did not make a correct classification. So in this case, we are going to use the majority filter to remove the noise. When the filter moves to this place, here's our majority filter. It's a cross shape. Here. It's a majority filter. So in the middle, it's a corn, right? So the 4 other pixels, here's a soybean, and soybean. So in this case, the majority actually is a soybean, right? Then in the upper layers, this place, the pixel in the middle, the value will change from corn to soybean. So if you look at this, you will not see the light gray colors here. In the input layer, there are multiple light gray colors here, light gray. But if you look at the output layer, there are not too many the light gray colors in this area, right? So the majority is in this example, we reduce the noise. Okay. So let's take a look at another example, edge enhancement. Edge enhancement is very popular in the remote sensing. In remote sensing, we often apply the edge enhancement to make the edge clear. So you can look at the upper half of the image. If you look at this, we have the light gray color here, the dark gray color here. That is the edge, right? We know there's one edge here, but the edge is not very clear. We want to make the edge more clear, so we are going to use the edge enhancement operation. Here, after the edge enhancement, that's the what it looks like. Here, if you look at this place, in the middle, that's the light gray. Here's dark gray. If you look at here, it's almost turned into white color, and the right other side is a black color. The left side is the white color. Right side is black color. It's more edges make it more clear, right? So that is the effect of edge enhancement. But how can we do that? We use neighborhood operation. Here, for the neighborhood operation, we learned that we can apply the majority, we can get the maximum, minimum, median, or average. So actually, besides that, we can also do some mathematical calculation within the moving window. like this. So the edge enhancement is to enhance the visual transition between the region of contrasting brightness. Okay. So in this case, we are going to apply a very special type of neighborhood operation. So here we also have one moving window, 3x3 moving window here. But this time we are going to do the mathematical operation in the moving window. Okay. Let's take a look at our input layer. Here's our input image. The right side, they are all the values, they are 2. The left side, all the values are 2, and the right side, all the values is 1. Okay, we know there's one edge, but the difference between the left side and right side is not that big. It's only the difference only 1, right? So if you use the image to look at to find the edge, it may not be easy to find the edge because the difference is too small. Let's look at the output layer. Output layer for the left side. Here, the value turn into 6. For the right side, at the edge, the value turn into -3. So the difference is 9, -3 to 6. Difference is 9, right? So if you look at the remote sensing image, the edge will be very clear because the difference is very large. That is the effect of the edge enhancement. Now let's take a look at how we did that. Now, let's take a look at our moving window, 3x3 moving window. If we apply the moving window here, we are going to do the calculation for the 9 pixels. And all the numbers here, they are 2 in the 9 pixels. The value, pixel value, they are 2. So here's our moving window, or sometimes you can call it kernel, or sometimes you can call it a moving window kernel. It's the same thing. Then we are going to do the calculation here. The value in the moving window, that's the weight. That's the weight. Okay. Here we're going to do calculate the product of 2 and the -1, and calculate the product of 2 and the -2, product of 2 and -1. The same thing for the product of 2 and -2 here, 2 and 13, and 2 and -2, 2 and -1, 2 and -2, 2 and -1. Okay. Now, after we calculate the product, then we're going to add them up. So it's here, 2 times -1, 2 times -2, 2 times -1, 2 times -2, 2 times 13 here, and 2 times -2, 2 times -2, 2 times -2, 2 times -1. So here, the sum is 2. Then we assign the pixel value in the middle of the moving window. The value is assigned as 2 here, this place. Okay. Then after we get the value for the first moving window, the center pixel in the moving window, then the moving window will move to right. Here, the moving window moves to this place, and we are going to repeat the same process. 2 times -1, 2 times -2, 1 times -1, 2 times -2, 2 times 2 times 13, 1 times -2. Same thing for the other 3 pixels. Then we get the product, we add them up. So here, the value is 6. So the value here in the center turn into 6. The same thing, the moving window move to this place, and we calculate the product, we calculate the sum, then the value is -3 here at this place. Right? So the same thing, we move to the right again, we calculate the product and calculate the sum, the value is 1. Okay. Then the same thing, we move to the next 3 rows here, move to this place, our new moving window, and we get the output, the net value is 2 here. That's the value for the central pixels. So if you look at this, after we applied the edge enhancement operations, the left side is 6 and the right side is -3. It's very clear. The edge is very clear, right? So that is the edge enhancement. So if you look at this, for the edge enhancement, we provide a very high weight or number to the center of the moving window. The center, the pixel in the center, it has a higher weight. Now in this example, it's a 13. Okay, like for all of the neighbor pixels, they have negative weight. So in this case, we can make the edge clear. So if we have another moving window, for example, we have another moving window like this, and all the pixels in the moving window have the same weight. For example, this one, 1, 1, 1, 1, 1, 1, 1, 1, 1. So in this case, that is not edge enhancement operation. So in this case, if we apply this kind of at the neighborhood operation, it will make the edge blur. Okay, for the edge enhancement, in the middle, it has to be a very large positive number in the middle and a negative number for the neighbor pixels. That's neighborhood operation and edge enhancement. Next, let's take a look at the zonal operations. We already talked about that. So for the zonal operations, it's based on defined zones, regions, or zones within an arrow. Like here's our input layer. We have the zonal layers here. And here, we have 3 zones, zone A. Here's our zone A here. Then we have zone B. There's zone B. Zone B. And we also have zone C here. Okay, sorry, here's still zone B. So then we are going to calculate the average or median or maximum or other type of statistical operations within each zone. Okay, so in this case, we calculate the average. So it's zonal mean or zonal average in this example. So for every number within zone A, so that is zone A here, zone A, here's zone A, A, it's also A. So I checked all the pixels in zone A. Now next step, we are going to calculate the average for all the pixels in zone A. Then we can see that the average value for this 1, 2, 3, 4, 5, 6, 7, 8. Yeah. For the 11 pixels, the average is 2.7. So all the pixels in the output layer in zone A, they have the same value, 2.7. Okay. Next, we do the same thing for zone B. Here's zone B. Zone B. It's a B here, B here, B here. Then we select all the pixels in zone B. Then we calculate the average again. So we get the pixel value for zone B. All of them, they have the same value in zone B. So zone C, the same thing. Okay, that's a zonal operation. But if we only have one zone, like every pixel is labeled as A. Here's A. Everywhere, every pixel has they are in zone A. Then all the pixels in the output layer will have the same value. So that's a global operation. Okay. Now I will give you 1 minute to calculate the value here. So in this example, we have three zones: zone 1 and zone 2 here, and zone 3. Okay, so we are going to calculate the zonal mean in each zone. Okay, so we already know the numbers in zone 1, numbers in zone C, zone 3, and now you're going to calculate the number, average number in zone B in the upper layer. You have 1 minute. All right, let's take a look at this example. So here, first we should know which numbers are in zone 2, right? So in this example, these 6 pixels, they are in zone 2, right? So in this case, in this example, we are going to calculate the zonal mean. So we select all the 6 numbers here, 8 plus 4 plus 4 plus 2 plus 6 plus 3, then divided by 6. So the value is, here's 12, 16, 18, 24, 27. 27 divided by 6. That'll be 4.5. Okay. So the number here is 4.5. It's the same for each of the 6 pixels. All right, that's all for our lecture today. It's pretty short, and for the lab today and tomorrow will be the zonal operations. So first, I'll give you one shapefile of the Oklahoma counties, and then I'm also going to give you the. Do I give you or you download? Like you need to get the distribution of forest and grassland in Oklahoma, and then do the statistics of the forest area in each county, in each Oklahoma county. So that is the zonal operation. Okay. All right. That's all for our lecture today, and I will not be in the lecture and lab in this week. I'm sorry about that, but I will see you next week.